Howdy everybody. Today we're going to tackle a combined circuit, one in which there are resistors in parallel that are also met with resistors that are in series. I set up a little circuit for you. I want you to make some predictions about what you expect to see in terms of the lighting and the lighting brightness. But let's just take a look at a schematic of the circuit. I'm going to use a power supply, not a battery today, so I'm just calling it voltage V. And I've placed one of those Christmas tree lights directly off the power supply, and then I've created a parallel branch that is after this. Again, the order in which you think about it doesn't matter. You can think of the current going first to the parallel branch and then coming back together and going through the series resistor R1, or you could think about current flowing first through R1 and then splitting through the parallel branch. Does not matter. Order isn't really relevant at all in a DC circuit. So let me go ahead and move the camera and show you the circuit and have you make a prediction. Here's my power supply. I've got the red connected to the positive and the black to the negative, but again, color really doesn't matter either. Let's follow the path of the circuit. Current, let's presume, comes out of the positive. It goes to this first bulb. Then it goes through this yellow lead. Now I put some rubber bands on there just to kind of make less of a mess. But it goes, all the current goes through the first resistor, R1, let's call it. And then there's a branch here. You can see that the current splits. And the green leads to one green bulb, the white leads to another green bulb. And those two come together here and go back to the negative terminal, the black, on the power supply. In a moment, I'm going to turn on the circuit and flick the switch up. But first, I want you to predict what is true about the brightness of the two bulbs that are in parallel compared to the brightness of the single bulb R1, we're calling it, that is in series with these parallel lights. Remember that the resistance of two resistors in parallel is less than the resistance of a single bulb. And in fact, if these are all the same, let's say 1 ohm, 1 ohm, 1 ohm, the two 1 ohm resistors that are in parallel together have a resistance of 1/2, right? We talked about that yesterday. The trick of two resistors in parallel, the total resistance is just half of each if they're equal. Also, recall that all the current in the circuit is going to go through this resistor. But when it gets to this junction and enters the parallel region, some of the current goes here and some of the current goes here. So make a prediction. I'll pause the video for a second. Okay, you've made your prediction, so let's go ahead and turn on the power. 2 parallel, 1 series. I wonder if that's what you predicted. Let's do a little investigating with the voltmeter and see what's going on. Coming out of the power supply, I have about 8.5 volts. But how does the voltage divvy up or split up in this particular circuit? And recall also that power, which is really what brightness depends on, is equal to the product of voltage times current. So how much of the 8.5 volts is across this first light bulb? Make a prediction. Holy smokes. The lion's share of the voltage, 6.6 of the 8.5, is right here. Only of the 8.5, only 1.8 of it, 1.7, 1.8 let's call it. Let me reverse the polarity so we don't have that negative. That drives me nuts. 1.8 volts here. Of course, parallel should be the same. So let's see if we get 1.8 here as well. We do. So we have 1.8, 6.6, And of course, 1.8 and 6.6 add up to 8.4, which is almost the source voltage, 8.5. Of course, we've talked about this before. There is some resistance in the wires themselves, and so we lose a little bit of voltage across each wire, but small compared to the bulb where the majority of the resistance is. I hope that was useful. We'll solve a problem or two with some numbers, but clearly when you have a series resistor connected to a parallel portion, you have most of your voltage drop here and all of the current. Most of the voltage and all of the current is going to result in brightness that's far brighter than, which is far brighter than the two in parallel. Again, most of the voltage and all of the current, 6.6 volts and all of I. And here we have half of the I in one, half of the I, half the current splits to here, and less voltage. So of course these are significantly less bright than the one that receives all the current and the majority of the voltage.